Next one, in antenna, whatever antenna you design, you have in antenna, you have far field and near field, right? So far field is the place where the signal becomes, where you can say the polarization becomes flat and whatever measurements you make are accurate. The variation in far field is going to be very, very little or almost zero. So we are going to see what is the far field of an antenna. Further, I am going to design an Yagi-Uda antenna. So see here, I am designing a Yagi-Uda antenna and I am showing the antenna. You know, a Yagi-Uda antenna will have three components, right? Reflector, director, and driven element, right? See here, you have a, I am designing a I am designing a 5-element Yagi antenna. Okay, so it is having 1, 2, 3, 4, 5. Okay, so for 5 elements, one element is placed at 0, other elements are placed away from 0, and one element is placed backside to 0. So whatever is in backside is called as reflector. Whatever in the front side, you call it as director. Okay, so this is the, you have three directors, one driven element and one reflector. Okay. Now the frequency is, assume the antenna is looking at 300 megahertz. Okay. So if you want to plot the radiation pattern, run the command, you can see 3D pattern. You can see a beautiful 3D pattern. So you know Yagi-Uda antenna is a unidirectional antenna. It will radiate along Z, and definitely you will have backload. But you see, major axis along Z, right? So majority of the radiation will be along Z. A very small portion occurs in the backside because of the back reflector. Because of the reflector you have at the backside of the antenna. And frequency you see 300 megahertz. Maximum value of the radiation pattern is 9.6 dBi. Okay, and the minimum value is minus 29.4 dBi. So dBi indicates dB isotropic. Isotropic antenna is a standard reference antenna. So all the measurements we make with respect to isotropic antenna. So when you do the conversion, you call it by the name dBi. Okay, plotting the polarization. So any antenna, the polarization parameter becomes very, very important. The polarization will give the orientation of the antenna. You can see the polarization pattern. So along whether it is right polarization, you have so many things. Linear, you have circular. In circular, you have right-handed, left-handed. You have elliptical polarization. In linear, you have horizontal or vertical. So here you can see the polarization is horizontal. So H it is given. So they have. So we have seen the H side of the polarization vector. So you can similarly view the V. You can see the RHCP and you can assume I'm giving V. So if you are giving V, you can view the vertical polarization of the antenna. You can observe the change in shape, right? Assume you are giving RHCP, right hand circular polarization. We'll see whether the RHCP is working. For this antenna, I think RHCP is a linear antenna, right? So RHCP will be almost like your H only. So only for circularly shaped antennas, you will have RHCP, LHCP, but for all these linear antennas, you will have H and V, okay, horizontal and vertical only. You can see how the horizontal and vertical polarizations look like H and V. Then 2D pattern, how to plot the 2 dimension of your radiation pattern. 2D means you are plotting both horizontal azimuth angle and vertical elevation angle.